we gonna need our calculators?
Yes.
All right, make sure you have a calculator.
Yeah, could I also have a calculator? God, Robbie.
Time to do these, but so much on the old ones for like
It was like no miss. It was just all one.
It was all on me too. You can say anywhere.
All right.
For that to happen. That's what you get.
Yesterday, we kind of took a very long way, I guess. It was very tedious to write out the possible factors of f of x. First of all, is it chilly in here? Yes. Is it a little cold? No.
It's actually hot.
Can I put the heat on for a little bit?
You don't need to do that.
I see Grace shivering over there. And just for a little bit. Just for a little.
Just a little. I know.
Grace, do you want my jacket? Okay. Yesterday, we spent quite a bit of time writing out the possible factors of this polynomial at the top, and then based off of those factors, we then took a look at the possible roots. It was very long, very tedious. We're going to try to shorten that up a little bit today because we like things to be a little quick. So from yesterday, can we list out the factors of the constant term from our equation at the top? What were the factors of -6 that we used yesterday? What are some numbers you can multiply together to get -6?
Positive -1.
Positive -1.
-6.
Positive
-3. Positive -2.
I like it. Okay, so we listed those from yesterday to help us write out possible factors. We also used the factors of the leading coefficient. So what are some numbers we can multiply together to get 3? 1 and 3. Okay, you can also do plus or minus in that case too. So what we're going to try to do today is find a little shortcut way to get these results from the table. So take a look at this. Now place each factor of the constant term over, okay, meaning we're creating some type of fraction. We're going to be dividing. Place the constant term factor over each factor of the leading coefficient. So we're going to take all of these factors from -6 and divide them by these factors of 3. So we're going to get a lot of different combinations. For instance, can we think about if we did plus or minus 1 divided by plus or minus 1? What would we get? Plus or minus 1, depending on the signs that you would choose to use. What about plus or minus 1 divided by plus or minus 3? Plus or minus 1/3. Okay, so we're going to go through all the different options. Now let's maybe move on to 6. 6 divided by 1, plus or minus 6. 6 divided by 3, plus or minus 2. Next we can do 3 divided by 1, which would be plus or minus 3. What about 3 divided by 3? Plus or minus 1, and we already have it listed. Okay, so don't worry about writing it again. So we can move on to plus or 2 divided by 1, which we already have listed as well. And then 2 divided by 3. Do these numbers look familiar? Where were those found? Yeah? They were all the possible roots that we did yesterday. So instead of trying to use these numbers to list factors and then get the roots from the factors, we can automatically use these numbers to go straight to the roots. Okay? And specifically by dividing the constant term factor over the leading coefficient factors. Okay, this is what's called the rational root theorem. Rational meaning fraction. Notice how some of these are fractions. Actually, all of them are fractions if you want to put the whole numbers over 1. So this process, this method, this technique is going to give us all of the possible real x-intercepts, okay, that we can actually see on our calculator. Now, they're going to be fraction ones, though, like 2, 2/3, 1/3, okay, actual fraction values. So let's go ahead and list that on the next page. We're going to write down what the rational root theorem actually gives us. So what we created is a complete and totally encompassing list of all of the possible rational, okay, fraction x-intercepts. For instance, I'm going to flip back. There's no way that this polynomial equation can have an x-intercept at 4 because it's not a part of this list. There's no way it can have an x-intercept of -10 because it's not a part of this list. So this is a total list of where your real graphable fractional x-intercepts would be. Bless you. Okay, so we're going to go ahead and write that down here. Rational root theorem tells us, or gives us, a complete list of fractional x-intercepts by dividing, bless you,
Thank you.
the factors of the constant term by the factors of the leading coefficient. I'll abbreviate LC for short. Have we seen this before, just out of curiosity? I'm seeing some yeses, some nos. Maybe you're more familiar with it as like P divided by Q or Q divided by P. Oh, that brings it back. Okay, we're taking the leading coefficient factors divided by, or sorry, the constant factors divided by the leading coefficient factors. Let's go ahead and take a look at this polynomial example right underneath it. Okay, we'll come back to the top in a minute. The example we did yesterday was factorable, so we were actually able to figure out what the exact x-intercepts were. But if you take a real close look at this equation, okay, we have 4 terms, so we could possibly do grouping to try to factor it. Unfortunately, if you tried grouping, the 2 leftover factors would not match. We know that's a condition in order for grouping to be possible. So unfortunately, we cannot do grouping with this equation. And it doesn't fit any other factoring technique that we've talked about. So unfortunately, this equation is not factorable. But we can still figure out where possible x-intercepts are located by this rational root theorem. So let's see if we can develop a list as to where those x-intercepts might be. So we got to take the factors of the constant term, which in this equation happens to also be -6 like it was yesterday. And we got to divide by the factors of the leading coefficient term, which is 6. All right, factors of -6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. What about factors of +6? It's going to be the same thing. Depending on which signs you would use, okay, they would actually be the same numbers though. Alright, So let's go ahead and go through all the different divisions that we could actually perform. We could do 1 divided by 1, so that'd be 1. 1 divided by 2. 1 divided by 3. 1 divided by 6. Then we'll move on to 2 up top. 2 divided by 1. 2 divided by 2. But we already have that listed. That's 1. We can do 2 divided by 3, and then 2 divided by 6, but that's already listed as 1/3. Next we can move on to 3 up top. So 3 divided by 1, 3 divided by 2, 3 divided by 3 is 1, 3 divided by 6 is 1/3. Alright, moving on to 6 up top. 6 divided by 1 is 6. 6 divided by 2 is 3. We already have that. 6 divided by 3 is 2. We already have that. And 6 divided by 6 is 1. And we already have that. So here's our complete list of possible fractional x-intercepts that we should be able to see on a graph. How many do we have? Can we count them? Yeah? There's 9. There's 9 numbers. There's actually 18, okay, because of the plus or minus. So we actually have 18 possible x-intercepts, okay, because you can do +1 or -1, depending on where you want to be on which side of the x-axis. So how do you think we can verify if these actually are x-intercepts or not? Yeah? We can divide them. Okay, synthetically divide them. So if we were to take one of these and treat it as our little outside number in synthetic division, and then we can use our equation, what should we anticipate if it's an x-intercept and we divide it out? Yeah? We get a remainder of 0, okay? Do we want to do synthetic division 18 times to see which of these are the true x-intercepts? No. That's what Descartes did. Okay, the guy that did the sign changes, okay, that's what he would have done. But because of modern technology, we're going to try this. Okay, so that's why you need a calculator.
God bless you.
Okay, bless you, yes.
God bless you.
What was that? So you know this calculator has the capability of finding the x-intercepts. But this is a way for us to kind of do it without a calculator. It would take us some time, right? Because you'd have to do it 18 times. But we're going to use this to kind of just get us a gauge as to where they are. Okay? So this is the same equation that we were just analyzing. We're going to go ahead and graph it, and just to get a good picture of it to see what it might look like. So y equals, clear it out, we'll type in the function. Let's see, maybe set your window -5 to +5, counting by ones. Bless you.
Bless you. Watch us sneeze.
All right, go ahead and hit graph. All right, we're going to draw a rough sketch. And we want to try to get as accurate, though, as possible with these x-intercepts. So I'm going to throw in some tick marks on the x-axis. If I read it left to right, this first x-intercept looks like it goes through a tick mark on my calculator, which would be -3. But notice how the other two do not go through tick marks. So we're just going to have to be a little careful on how we graph it. And we'll just draw a rough shape connecting those dots. Okay, we just want to be accurate with those x-intercepts. So based off the calculator, does it seem like we have an actual x-intercept that's easy to identify from this list? This one went through a tick mark, right? So it should be a whole number. Okay, so it looks like we have -3. Let's go ahead and confirm that by using synthetic division. Okay, so we'll go to the bottom down here. We'll do -3 as our little outside number. And then we'll take the coefficients from our equation and go through our division process. Do we need a reminder on synthetic division? No? We're good? Okay. Remainder of 0. Looks good. All right, so we have an x-intercept at -3. We have 2 more to verify. So on our calculator, let's go ahead and hit the trace button. You might have to hit the arrows a few times till you see your little cursor. And we're going to try to get that cursor as close as we can to an x-intercept. I can't really get it on it, but it's still pretty darn close. And it looks like -0.64-ish. Is that close to one of these possibilities that we listed? Can we convert decimal to fraction? Are we familiar with what some of these are as decimals? Yeah. -2/3. Okay, that's 0.66666666. That's really close to 0.64. So let's go ahead and do -2/3 as our outside number. Now, since we already did synthetic division once, okay, because we know -3 goes in evenly, let's go ahead and use 6, 1, and -2, okay, as these coefficient values. You could use the original ones again, but notice how this is just 3 numbers instead of 4. So it's one less value that you'd have to worry about, but you can use the original ones. All right, let's test it. So -2/3 times 6. -2 times 6 is -12. Divide 3. -4. Oh wait, that goes here. That goes there. Okay. Then we'd get -3. -2/3 times -3. +2. Remainder 0. Check. All right, so we'll add -2/3 to our list of x-intercepts. Let's go ahead and see if we can find the third one. So on your calculator, move it kind of close to where the x-intercept might be located. We get 0.53. At least that's the closest I can get it. You got 0.5. You were able to get it on exactly? Yeah, good. Okay. So 0.5. Notice how that's a part of our list. We'll go ahead and do 1/2 as our little outside number. And again, you can use the original coefficients from the polynomial, or you can now use 6 and -3 because those are the leftover coefficient or the quotient values. Oh, divide by 3. Good check. So then this would be 2 and -1. Half of 2, 1. Remainder 0. Because if you wrote this as so this would be x plus 2/3 as a factor, but you can slide the 3 out. And when we were doing the synthetic division section, if we had a coefficient in front of the x, we had to divide the quotient by that value. So we'd have to divide by 3. Actually, I think if you left it as 6 and negative 3, it would still work out. Okay, so don't get me wrong, it would still work out, but the actual quotient value should be 2 and negative 1. Okay, if you were to rewrite it, but it should still work out either way. That's what's nice about it. It should always work out. Okay. All right, so we went ahead and confirmed that out of all of these 18 possibilities, these are the 3 actual x-intercepts. You still would have got to the same result if we didn't have the calculator. You just would have had to gone through all 18 possibilities by using synthetic division. I don't want to do that, so that probably means you don't want to do that, right? That's why we're going to use our calculator as a guide to help us get a guess as to which one of these or some of these we should check. All right, let's go ahead and try another one. Let's first develop our list of possible x-intercepts. We have factors of 10 over factors of 6. What are some factors of 10? 1, 2, 5, 10. Factors of 6. 1, 2, 3, 6. Let's find our possibilities. 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 6. Move it on to 2. We'll have 2 and 2/3. 2 divided by 2 and 2 divided by 6 are already listed. Move it on to 5. We'll have 5, 5 over 2, 5 over 3, 5 over 6. Move it on to 10. We'll have 10 and 10 over 3. 10 over 2 and 10 over 6 are already listed in their simplified form. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2, 24 possibilities. Okay, we are not going to do synthetic division 24 times. We're going to graph it and try to estimate which ones we should actually check and verify that they are the true x-intercepts. So on your calculator, we'll go ahead and type in the original function. Did it look like we have an x-intercept that's very nice, like a whole number we could automatically check? 2. Yep, that one went through, looks like a tick mark, and that would be a positive 2. It's on the right-hand side of the origin. Let's go ahead and use 2 as our outside number. All right, synthetic division, we can definitely do. All right, I got remainder 0, so we're good. Let's go ahead and hit trace, and we'll move our cursor to try to find another one. So this one, I can't really get it on the x-axis, but I'm pretty close to it. 0.32. Is there a list that we have, or a number in our list that's pretty close to that? 0.32. Can we choose one? A third. Okay, that's 0.33333. That's pretty close to 0.32. And this one's also positive. So let's use 1/3 as our outside number. You can use the original coefficients, or you can now use the quotient values. 6, 13, -5. It shouldn't matter. All right, drop the 6. A third of 6 is 2. A third of 15 is 5. Remainder 0. Okay. Now, realistically, we should divide these coefficients or quotient values by 3. Okay, if you wanted to do another round, but if you forgot to do that, it should still work out. Okay, so it's okay if you forget. Let's try the other one. Let's move our cursor. All right, this one's kind of difficult, at least with the window I have. So when my cursor's up here, I'm at -2.45, and if I hit my arrow one more time, I'm at -2.55. So do we have an x-intercept somewhere between those two numbers? -2.45 and -2.55. Can we circle it on our list? 5's half. Okay, so that's 2.5. Okay, 2.5 as a fraction. And notice how this one's negative. So we will use -5/2 as our outside number. If we take the previous quotient values instead of the original coefficients, okay, we'll have 2 of them this time instead of 4, we could write 2 and 5 when we divide by 3. So drop the 2, multiply, looks like we get a remainder of 0. So we'll say the x-intercepts are 2, 1/3, and -5/2. Instead of doing synthetic division 24 times, we're using some technology to help make our life a little easier. Say it again.
Mr. Konjac made us do it
Every time.
every time. I'm actually mad about this.
Really?
Yeah.
So he would have made you do all 24?
Yeah. Oh yeah.
Yeah. For a test too? Okay.
We would say for 3 class periods after.
Trying to check every single one. Okay. I'm trying to make your life a little easier.
Thank you.
You're welcome. Okay. Let's try another one. Notice how 4 terms, if you tried to factor, you'd have to do grouping, but anticipating what you would get, the remaining factors would not match. Okay? That doesn't mean we don't have any x-intercepts, it just means we can't find them by factoring. So we're going to try another technique. We're going to use this rational root theorem to help us give us an idea as to what the x-intercepts could be. So we need factors of 3 divided by factors of 18. Factors of 3, 1 and 3. Factors of 18, 1, 2, 3, 6, 9, 18. All right, let's do the actual division of these factors to get our list of possible fractional x-intercepts. So we'll have 1, 1/2, 1/3, 1/6, 1/9, 1/18. If we move on to 3 up top, we'll have 3, 3/2. 3/3 is already listed, 3/6 is already listed, 3/9 is already listed, and 3/18 is already listed. So we're done. 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 options this time. We're going to make our life a little bit easier and graph it to get an idea as to where these x-intercepts actually are. So 18 x to the third plus 15x squared minus 16x plus 3. So if you look at the graph, it seems like we only have 2 this time. Notice how this x-intercept is bouncing, so multiplicity of 2. And I don't think either one of them landed on a tick mark. Am I right? Did I view that correctly? Okay, so we're not going to have any whole numbers. We could automatically eliminate 1 and 3 from our list. So let's go ahead and hit trace, bring up our little cursor, and try to get as close to an x-intercept as possible. Let's see. I got 0.32 as an x value that's really close to where the x-axis is. So from our list, that's close to 1/3, 0.33333. So let's go ahead and use 1/3 as our outside number. A third of 18, 6. A third of 21, 7. A third of -9, -3. Remainder 0 looks good. Alright, so x-intercept, we've confirmed 1/3. Let's go back to our calculator, move the cursor, try to find the next one. Alright, the closest I could get is -1.49, which is probably really close to -1.5. So from our list, that would be 3/2. Alright, now you have options. You could use the original coefficient values from the function, or you can use the quotient values. If you use 18, 21, and -9, it'll still work out. Your numbers might be large, but it'll still work out. You really should divide these by 3, though. Make the numbers maybe a little smaller, easier to work with. So we can do 6, 7, and -3. -3/2 times 6. -9. -3/2 times -2. 3. Remainder 0. So we confirm -3/2 is our other x-intercept. We doing okay? Can we do one more? We'll end it on a good note. Okay. Let's try our last one. Okay. 4 terms. If you wanted to factor, you would try grouping. Unfortunately, hindsight, not going to work out. Okay, the little pairs wouldn't match. So let's try our rational root. Factors of -6 over factors of 8. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Factors of 8. 1, 2, 4, 8. Alright, so we develop our list. Plus or minus 1, plus or minus 1/2, plus or minus 4, plus or minus 1/8, plus or minus 2. That's actually it from that one. Plus or minus 3, plus or minus 3/2, plus or minus 3/4, plus or minus 3/8. And I think we'll end with plus or minus 6. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times 2, 20 possibilities. 20 times, yep. Not today, at least, right? X to the third minus 6x squared minus 17x minus 6. Graph. All right, so if you watched it pretty carefully, this little kind of hump or bump here actually does go above the x-axis. Okay, maybe you want to graph it again just to see that. So we actually have 2 here. This is not a multiplicity of 2. We have to be careful. Let's hit trace. Actually, looking through it, it seemed like this one went through our tick mark of 2. So maybe we'll just start things off with that one. I got a remainder of 0. Looks good. All right, let's check out these other 2 that are really close together on the left-hand side. So my first one, really close to negative 0.42, negative 0.53. What do we think? Is there something in our list that's really close to those 2? Negative 0.42, negative 0.53. We're thinking negative 0.5. Okay, let's try it. We can use 8, 10, and 3. All right, I got remainder of 0. You really should divide these quotient numbers by 2. If you forget to do that, it will still work out, but you really should divide them by 2. All right, let's check out the next one. If I move my cursor, negative 0.74, negative 0.85. Do we have something close to those from our list? What about 3/4? 0.75? Okay. So negative 3/4. We'll do 4 and 6 if we divide those by 2. Looks like remainder of 0. So x-intercepts, 2, negative 1/2, negative 3/4. There we go. Okay. Now, this is going to bring in something that some of you may have remembered that we've done at the beginning of the year. Are we familiar, or I know we should be familiar with it because we did it, but the better question is, do we remember how to find x-intercepts on our calculator exactly?
Like the trace.
The trace, yeah. If you do second trace, option 2 is 0. You got to pick that left point, right point, take a guess. You can find them exactly. That way you know which one of these to actually use to test using your synthetic division. Okay, so you don't really have to guess, if you will. You can find them exactly. But I do want to see this work. I know your calculator can, is that what you're going to say? Yep. I know your calculator can do it for you because it has that capability. But I need to know that you understand this method, this technique, okay? For those of you that had Mr. Konjak last year and you didn't have a calculator, you would have had to done this 20 times, okay? I want to see that you understand the connection here between this rational root theorem and how it relates to these x-intercepts. So I'm giving you an inch, okay? Don't take a mile. Do you know what I mean by that? I'm trying to be nice by letting you use this, but I still want to see the work. Deal?
Deal.
Okay. Sounds good.
Hey,
So much easier.
Like 5 people use that in their class on